Now, the Doppler effect is usually associated with sound. We hear it all the time, from NASCAR races to ambulances flying by us to hearing horns on the street. But Doppler effect can also be used to calculate and see how light changes as well, observed frequency versus emitted frequency. However, our ears don't hear light, so frequency is not really used when we're looking at the Doppler effect of light. Typically what we'll see is wavelength, because wavelength is what our eyes interpret as the various colors on the visible spectrum. So here's a quick question. Looking at hydrogen atoms in a distant galaxy. They're going to emit a wavelength of 656 nanometers, so this is what they're emitting. Now, the light received on Earth is measured to have a wavelength of 689 nanometers. We're going to calculate the speed of the galaxy. Now, one interesting thing here is we notice that our wavelength increases. We go from 656 nanometers to 689 nanometers. This is called redshift. The light is becoming redder. So red on our visible spectrum is 700 nanometers. So as we get closer to red, that 700 nanometers, we have redshift. This is going to indicate that this galaxy is moving away from us. Okay. So this galaxy is going to be moving away from us. We just need to know by how much. So that's the speed that we're going to be looking for. So now to understand this formula up here, and this is how you'll see it in your data booklet, we have delta lambda, so delta being change in lambda, or change in wavelength, over wavelength, equals change in frequency over frequency, is approximately equal to the speed of the source over the speed of light. Okay, well, speed of light is a constant, and so this is a rough estimate that helps us calculate the speed due to our changed observed and emitted wavelength. Okay, so here we're going to do delta lambda over lambda is approximately equal to V over C. We're not going to use frequency here. It doesn't make sense to use frequency. We're not given frequencies. So to find V is just a simple case of rearranging delta lambda over lambda times C. Now the only thing we have to worry about here is that our speed of light is given to us in meters per second, and we are given wavelength in nanometers. So 1 nanometer, so nano is a metric multiplier, that's going to be the same thing as saying 1 times 10 to the negative 9th meter. So that is a billionth of a meter. So we're talking really, really tiny wavelengths here. But this is what our brains interpret. So our change in wavelength, we're going to do 689 minus 656, 6. And we're going to multiply this whole thing by 10 to the negative 9th. So we go from nanometers to meters. And then we're going to divide that by another wavelength. So we have 2 wavelengths given. So the trick to remember here is that this is going to be the source wavelength. So what did our wavelength emit at the source? And that's the 656. Once again, multiplying by 10 to the negative 9th. So we can go from nanometers to meters. Then we're going to multiply by 3 times 10 to the 8th, and that's our meters per second. That is our speed of light. If you plug that into a calculator very carefully, watch your exponents, you should arrive at a number of 1.5 times 10 to the 7th meters per second. And that will be our final velocity. So, to recap, this is the speed of a galaxy where hydrogen atoms are emitting at 656 nanometers, but on Earth we see them as 689 nanometers. This shift is that redshift. So this galaxy, redshift, moving away. This galaxy is moving away at 1.5 times 10 to the 7th meters per second away from planet Earth.